Good morning. In Unit 1, Part 1, we shall look at observations and measurements. These are the foundation on which scientific theories are built. The scientific method. What is the scientific method? Well, if you look at the chart, you'll see that everything starts with observations. We need to make one or more observations, and then these observations allow us to come with some sort of explanation of the phenomenon we're interested in. And this explanation, if you will, a tentative explanation, an untested explanation, is called a hypothesis. A hypothesis should be testable. In other words, we should be able to test the hypothesis by doing some experiment and predicting the outcome. If we can predict successfully the outcome of an experiment, and we can devise some more experiments and keep on predicting the outcome successfully, the hypothesis becomes a tested hypothesis, and we call it a theory. A theory is a model of a certain phenomenon. In other words, it explains why the phenomenon occurs. A theory is usually tested further by making more experiments, see what they predict, and then see the outcome. If the outcome is not exactly what we expect, we may modify the theory so that when we do the experiment again, we can predict the outcome more precisely. A successful theory is an accurate and predictive description of the natural world. Observations. Observations are of two kinds. There are qualitative observations, which entail a description. For instance, color, taste, shape, whether an object is cold or hot, how we perceive it. And such observations are quite useful. We make quite a few of them. In many sciences, they are absolutely crucial. However, they're usually not sufficient to come up with theories. Somehow, if an object is hot and cold, one would like to be able to assess the relative coldness or hotness of that object. In other words, we must be able to somehow use a number to describe that relative hotness or coldness. And this now brings us to a quantitative observation, which involves invariably a number and a unit or scale. So that, for instance, we may say that, oh, this object feels cold to the touch. That's a qualitative observation. But if we say this object has a temperature of 2 degrees Celsius, we've made a quantitative observation. The 2 is the number, and the degree Celsius is the unit. It's part of a scale. Quantitative observations are usually referred to more simply as measurements. Units are very important and are an integral part of a measurement. Without the unit, the measurement is useless. If, let's say, you tell someone, this stick is 10 long, you haven't really said anything. It's 10 what? Is it 10 inches long, 10 centimeters long, 10 feet long? And this is why it's very important to always make sure that a number is followed by a unit when it describes a measurement. There are many systems of units, too numerous to mention here, but we are all familiar with at least two of these systems. The English or imperial system, which was developed, as the name implies, in England, and the metric system, which was developed in France. Now, the English system is very inconvenient for scientific work in that its multiples, or rather as one goes from a small unit to a large unit, the multiples are not decimal. In other words, they are not related by powers of 10. For example, there are 12 inches to the foot, there are 3 feet to the yard, and there are 1,760 yards to the mile. Even these numbers are sometimes difficult to remember, let alone do calculations with them. On the other hand, in the metric system, the multiples are decimal. There are 10 millimeters to a centimeter, 10 centimeters to a decimeter, 10 decimeters to a meter, 10 meters to a decameter, etc. Now, so the metric system is more convenient, obviously, but even using the metric system, there are several subdivisions, and they were used by different branches of science. For instance, physics and chemistry had made different use of the metric system. In chemistry, one used the CGS system, which means centimeter gram second, and in physics, one used the MKS system, which stands for meter kilogram second. And that again made it difficult to communicate between the two branches of science. And so in 1960, the Conference on Weights and Measures established what is known as the International System, which is known by the initials of the French name. It's called the SI system, which stands for Système International d'Unité. And this is essentially a completely metric system. It's very much what the physicists used. It's an MKS metric system, and it's been adopted by practically every country in the world, as far as I know. For science, of course, not for all disciplines, not necessarily for engineering or for everyday work. It turns out that all quantities that one has come across can be expressed in terms of 7 fundamental quantities. The ones that we're going to use in this course are shown here on a green background. Now, each fundamental quantity has a base unit. For instance, mass has a base unit called the kilogram. The base unit of length is the meter, the base unit of temperature is the Kelvin, and so on. Each base unit has a symbol, and the symbol has to be written exactly as specified. So, just to give you an example, for kilogram, the symbol is kg, and it has to be written exactly as shown on the left-hand column here. It's a lowercase k and a lowercase g. Sometimes you see in supermarkets that kilogram is written as capital Kg. That in science would be wrong. So, what do we have to know of this table? Well, we have to know the quantities, the fundamental quantities, the 5 that are shown on a green background, their respective base unit name and the respective symbol. Now, obviously, these quantities are very specific and simple ones, you might say, and in fact we know that all other quantities can be expressed in terms of these fundamental quantities. What we mean is that in terms of combinations of these fundamental quantities. And the other quantities are called essentially derived quantities, if you will, and the units are called derived SI units. Derived SI units are obtained by combining base units. For instance, we can combine length with itself to form an area or a volume. Area is simply length squared, and volume is length cubed. Other quantities require the combination of different fundamental quantities. So, for instance, both force and energy require a combination of length, mass, and time. Many of these derived units, in fact the majority, have specific names. So we can say that the derived unit of force is the Newton, and the derived unit of energy is the joule. Now, all of these units have a fixed size and therefore are not always useful immediately in describing anything that comes our way. For instance, if we want to describe a length that's perhaps 1,000,000 times larger than the base unit of length, the meter, or 1,000,000 times smaller, how do we do that? Well, we could use simple scientific notation, and if we mean 1,000,000 meters, we could write 1 times 10 to the 6th meters. Or if we mean 1,000,000th of a meter, we would write 1 times 10 to the minus 6 meters. And that's perfectly correct. However, sometimes it's simpler to speak or to write a quantity without this scientific notation. And in order to do that, SI prefixes have been introduced. You can see a series of prefixes. They are certainly not exhaustive. You can go much higher than 10 to the 9th and much lower than 10 to the minus 12. And actually, I have a document uploaded on LEA, which gives you many more prefixes and symbols, but basically we shall have to know only the ones you see on this slide, and we can actually omit or not know the symbols hecto and deca. They are not much in use in North America. They are used in Europe, but not in North America. Or if you want to make it more complete, what you learn, you could include them. But the ones whose names are given in green here are absolutely necessary to the use in any science, and so you must memorize them. You must memorize not only the prefix, the name of the prefix, but the symbol for the prefix and the exponential value for that prefix, so that if you have a kilobyte or a kilometer, it means 10 to the 3rd power meters or 10 to the 3rd power bytes. In other words, 1,000. So you can also substitute, if you write 2 times 10 to the 3 meters, you can substitute by writing, you can substitute the 10 to the 3rd power by k, and so you can write 2 kilometers, km, and so on. So it's very important that you memorize these prefixes and their symbols and their values. In other words, the whole table. It may seem like a tall order, but it's not. It's very easy, especially if you notice that the unit would be the meter, So as you go from meter up, each unit above the meter is related by a power of 10 to each other. And at the beginning, for the first 3 increments, you go by 1 power of 10, 10 to the first power, second power, third power, and then you go by 3 powers of 10. Similarly, as you go to smaller units, the first 3 steps are related to each other by 1 power of 10, but from then on it goes only by 3 powers of 10 at every increment. So you see, there's a method to it all, and all you have to do is remember how it works. Again, you must remember the symbols. Here there's mega, that's a capital M. You can see that milli is a lowercase m. So when you come to micro, we run out of letters in the Latin alphabet, and then we go to the Greek alphabet, where we use the letter mu, which is Greek letter m, for micro. So if you want to write a micrometer, you write mu m. And we'll see examples of that as we go along. Units of volume. The most commonly used metric units for volume are the litre and the milliliter. Now, these are strictly not SI units. The SI units corresponding to the litre and the milliliter would be the cubic decimeter and the cubic centimeter. And this shows you essentially the relationship between a cubic decimeter and a cubic meter, which is the SI base unit of volume. And you can see here, if you look at this and observe it a little more carefully and count the number of cubes in this slice here, and then you multiply that by 10 for the other slices, you'll see that in fact there are 100 times 10 or 1,000 cubic decimeters in 1 cubic meter, or 1,000 liters in 1 cubic meter. And because the cubic decimeter, or because the liter is really so similar in size to what a cubic decimeter would hold of water or milk, we've accepted the liter and the milliliter as a substitute for cubic decimeter and cubic centimeter, but we shouldn't forget that it is the cubic decimeter and the cubic centimeter that are the SI units, and not the liter and the milliliter. However, in North America, the liter and the milliliter are used freely as substitutes for the actual SI unit, and it is tolerated by the SI, if you will, system. If you look at food containers imported from Europe, you'll see that the liter and the milliliter are never mentioned. Everything is always described in terms of cubic decimeters and cubic centimeters. We don't have to justify a conversion between cubic decimeter and a liter. Normally, we just accept a liter as another name for a cubic decimeter, and a milliliter as another name for a cubic centimeter. It is important to recognize that every measurement has a certain degree of uncertainty. And let's look at an example. In this illustration, we see a board, that's this upper part here, the brown one, and we want to measure its length. And we're given a yardstick, or more precisely a meter stick. So this is a stick that's exactly 1 meter long, and it has no other divisions on it. So obviously we're not going to obtain a very accurate or precise measurement, but we can estimate the length of the board. We could say that this is really the halfway mark on the meter stick. Therefore, we can see that this board is more than 0.5 meters. It's probably somewhere between 0.6 meters and 0.7 meters. We're not exactly sure. And so we can write that the board is approximately 0.6 to 0.7 meters. Can we improve on this measurement? Yes. If we get a better meter stick, one that is divided into more intervals, and so we could divide this meter stick into 10 equal intervals, each one 1 decimeter long. And now we measure once again the board, and we see that indeed it is between 0.6 and 0.7 meters long. So our estimate was good. Now we can refine it a bit by saying, all right, we can see it's between 0.6 and 0.7, but we can also estimate the length of it a bit better, which all you have to do is essentially divide this interval between 0.6 and 0.7 into 10 parts, mentally that is, and then we see that the stick doesn't quite reach the half mark here. That is, it's less than 0.65. Therefore, it could be 0.63 or 0.64. It's not likely to be 0.65. And I'll just take one of these two values. I'll say it's 0.64 approximately. I can still improve a bit this value, or the, if you will, the resolution or precision of my measurement, by now dividing each of these decimeter intervals into 10 more parts. In other words, I divide them into centimeters. And now, if I measure once again the board, I see that indeed its length is 0.6 meters, 0.61, 0.62, 0.63, 0.64, something. So the 0.64 was a good estimate, but now we can improve on it by saying, all right, again, I look for the middle point here of the interval. So that's the midpoint here. This is less than the midpoint, so I'll say, all right, it's probably about 0.643. You might say it's 0.644 or 642. It's hard to tell. It's an estimation. And therefore, I'll just stick to my value of 0.643. Can I improve upon that? Well, in theory I can. I can still subdivide these now fairly small intervals, 1 centimeter long, into 10 more equal intervals, each one 1 millimeter long. And I'll do that in the next illustration. And I can still measure this up to a point. I probably need a magnifying glass, but if I take my magnifying glass, I see that the value I get is 0.642, not 643. So this is not such a good estimate, but I mean, some people might have gotten 2, some people might have gotten 3, some people 4. That's an uncertain value. You can see there's always an uncertainty in the measurement. Well, here the uncertainty now is no longer the third decimal, it is in the fourth decimal. We're going to say it's 0.6425 or 6.424, something like that. So let's write something down. Let's say it's 0.6423. Really, it was very difficult to estimate this last digit because at this point now, the thickness of the end of the board, which is essentially it's really not smooth, it's fairly rough, and the roughness is of the order of 1 millimeter. In other words, it's of the order of the smallest division on the scale, or the smallest increment, as the proper term is. And therefore, there's not much point going on and on. So what have we seen here, really? We see that as we subdivide our meter stick, we get more and more decimals in our measurement. But perhaps we haven't noticed that there's a pattern to it. If the smallest subdivision or increment is the whole unit, 1 meter, then our estimate is to 1/10 of a meter. In other words, one place better than the smallest increment. If the smallest increment is 1/10 of a unit, a decimeter here, then our estimate or last figure here is to 100th of a unit, and so on. So in every case, we can estimate our value for a measurement to 1 decimal place better than the smallest increment on our scale. And this is an important rule, so that we can say that whenever we measure an object, whether it's length or mass or any other physical characteristic you can think of, we always should record our measurement to 1 place better than the smallest division on the scale. And that last place is always uncertain because it's an estimation, and different people may estimate it differently. And so we come to what is known as the significant figures of a measurement. So we've seen that a measurement always has some degree of uncertainty, and that the last digit that we record is an estimated digit, which is called uncertain. Whenever recording the results of a measurement, one should always record all certain digits and 1 uncertain digit. Together, these are called the significant figures of the measurement. In this slide, we see some scales, which could be thermometer scales. And we would like to be able to read the correct temperatures and then express these values to the appropriate number of significant figures. How do we go about this? Well, first step is to figure out what the increment on the scale is. And so, if we start with the scale on the left, scale A, the way to figure the increment is simply look at divisions to which numbers are attached. For instance, the 30 division here and the 20 division here, and then count the number of subdivisions in which this larger interval has been divided. So the difference in temperature between the top value here and the bottom here is 30 minus 20, which is 10. And if we count the intervals in which the interval has been subdivided, we see it's also 10. So we just divide the 30 minus 20, by the 10 intervals in which it has been subdivided, and 10 over 10 is 1. Therefore, we deduce that the increment on this scale is 1 degree. That's the first step. So right away we see that the thermometer has risen above the 21 mark, the liquid in the thermometer, that is. And we could estimate this to be perhaps 21.2. Some might say it's 21.1, some might say it's 21.3, but we can't be any more precise than that. And therefore, I see it as 21.2, and I'll write therefore here my value for this temperature as 21.2 degrees. Is it to the appropriate number of significant figures? Yes, it is, because the smallest division on the scale, or the increment of this scale, is 1 unit, 1 degree, 20, 21. And I'm expressing my temperature to 1/10 of a degree. Therefore, I have 2 certain digits and 1 uncertain digit, which essentially gives me 3 significant figures. Now, in B here, the scale is exactly the same as in A. There's not much else to say, so we can read immediately this value as 20, 21, 22. Should we write 22? No, we shouldn't write 22, because we have exactly the same scale in B as in A. Therefore, we could also estimate 1 more place than the smallest increment. 22 is 22 units. Therefore, I should still be able to record my number to the same number of decimal places as in A. and therefore I would have to write this as 22.0. You can see why, because obviously if my liquid here had risen above the mark, let's say by maybe 0.2, 0.3, or maybe halfway, I would have written this as 22.5, and therefore I can obviously estimate a tenth of a degree. And here I estimate my tenth of a degree to be 0. In other words, it's 22.0. In fact, 22.0 means 22.0 plus or minus 0.1. One tenth of a degree, plus or minus 1/10 of a degree. That's the range of my estimation. In other words, I could say that this temperature here is 21.9, 22, or 22.1. It's anywhere in the range 21.9 and 22.1. The range is 2/10 of a degree. But had I written this as just 22, that would have meant 22 plus or minus 1, and the range would have been really 2 degrees, not 2/10 of a degree, because then my range would have been between 22 minus 1, which is 21, and 22 plus 1, which is 23. 23 minus 21 is 2. So it's very important, as I say, to record your measurement to the correct number of significant figures, because otherwise you appear to be really sloppy in your work. Finally, let's look at the last scale here, which is C. And we see that now this scale is a little different than the previous ones. Each smaller interval, which is 1 degree, it still is 1 degree, has been subdivided into 1/10 of a degree, which means now that we should be able to estimate our measurement to 1/100th of a degree. And we can see it in the next reading here. We can see that perhaps we need a magnifying glass to see better, but essentially we can see that the liquid has risen to 22, and then it seems to have risen to about 1 notch more, which is 1/10 of a degree. It might be slightly above that, so it might be 22.10, it might be 21.12, 22.11, and so on and so forth. With my magnifying glass, it still looks as if it's flush with the first subdivision here, the first small increment, and therefore I'll estimate my reading to be 22.1 knot. You see, I have one more decimal now, because obviously if the liquid here had risen to exactly halfway between two of the smaller marks, this would have been 22.15. So clearly I can estimate one more place then with the scale here. I've added one subdivision, I've divided this interval into 10 parts, and I'm able to read or to obtain a value which essentially is to one more decimal place. Again, I have one uncertain figure here and 3 certain ones. Those are the significant figures of the measurement. How do we know which digits are significant and which aren't? And as we'll see, it depends on the sort of digit we're looking at. For instance, there's a rule for non-zero integers, in other words, the integers from 1 to 9, and there are other rules for zero integers, depending whether they are leading zeros, captive zeros, or trailing zeros, and finally, there's a rule for exact numbers. So let's look at those rules in detail. Non-zero integers always count as significant figures. As an example, you could say that 3,456 has 4 significant figures, simply because every integer is significant. Zeros. Leading zeros do not count as significant figures. And what are leading zeros? Leading zeros are zeros that come to the left of the first non-zero integer. So in this case here, these are leading zeros, these two, and they do not count as significant. So we say that this number here has 3 significant figures. Captive zeros always count as significant figures. In the example shown here, the number 160.07 has 5 significant figures, and the 2 zeros shown in the number, those 2 zeros here, are captive zeros. Captive zeros simply are sandwiched between non-zero integers. That is, they have at least one non-zero integer on their left and one non-zero integer on their right. And of course it stands to reason that if this digit here is significant, then this one here, which represents 10 times larger order of magnitude, must also be significant. Or in other words, if we've actually accept this as our uncertain digit, then this one must be certain one, and so must this one, of course. Trailing zeros. Trailing zeros are significant only if they come after a decimal point. In this example, 9.300, there are 2 trailing zeros, you can see them here, and there are 2 non-zero integers, so this number 9.300 has 4 significant figures. Trailing zeros, as the name implies, are zeros that come at the end of a number, and they're only significant if they come after a decimal point. So let's look now at an exercise to see if we can essentially apply the rules. How many significant figures are in the following numbers? Well, the answers are not difficult. All you have to do is recall the rules that we've just learned. So the first number here, 0.04550, should have really 4 significant figures, because it has 2 leading zeros which are not significant, and we have a trailing zero which comes after the decimal point, and after, of course, the last non-zero integer, and therefore it is significant. So the 4 significant digits are the 4, the 2 5s, and this 0 here. 100 pounds. The way this is written is really a poor way of expressing it, because the way it's written, this quantity has only 1 significant figure. Remember that trailing zeros, such as these 2 here, are not significant if they don't come after a decimal point. In this case, they're coming really before or to the left of the implied decimal point, which should be here. This is where the implied decimal point should be, but it's implied, it's not really written, and therefore this number has only 1 significant figure. I say it's poorly written because obviously we don't mean 100 pounds plus or minus 100. We mean 100 pounds usually plus or minus 1 or 2 pounds. So really what we mean is 3 significant figures. If we are to write it as 3 significant figures, we should do it either by putting a decimal point immediately after the number, which is not bad, but it's not very good either, because it could be confused with a punctuation mark, a period. The best way, if we mean 3 significant figures, is to write it in exponential notation. In other words, write it as 1.00 times 10 to the second power. Then the 1.00 have 3 significant figures, and the 10 to the minus 2 gives the value of 100. The next number, 1.05, has 5 significant figures, because again, the zeros here, the first zero is a captive zero, and actually both zeros are captive zeros when you look at them, and therefore all digits here are significant. And finally, 350.0 has definitely 4 significant figures, because this zero here is a trailing zero. In fact, both of these zeros are trailing zeros, but one comes after the decimal point. Since it comes after the decimal point, it is significant. And again, if a tenth of a unit is significant, a whole unit here has to be significant. You cannot measure something to a tenth of the unit and then say that the unit itself is uncertain or insignificant. And so this one has 4 significant figures. Exact numbers have an infinite number of significant figures. How do we get exact numbers? We said all measurements have a certain degree of uncertainty. That's true, but we do have definitions, for instance. 1 inch equal to 2.54 centimeters exactly. That's by definition. It's been set to be this way. And when you have exact numbers, they do have an infinite number of significant figures, as we'll see shortly. Another way of obtaining exact numbers is by counting. Counting is not a measurement. And when you count something, even if 10 people or 20 or 30 people count a number of objects, they all should get the same number, with no uncertainty whatsoever. Let's say one makes several measurements, and each one has a different number of significant figures. These are combined in a mathematical operation, and the question is, how many significant figures should the result have? Well, there's a rule for multiplication and division, and another rule for addition and subtraction. For multiplication and division, the number of significant figures in the result equals the number of significant figures in the least precise measurement used in the calculation. For example, if we divide or multiply, in this case, 6.38 times 2, and using a calculator, we obtained 12.76, which now, according to the rule enunciated above, we have to round off to 2 significant figures. And so the result is 13. Why do we use only 2 significant figures in the result? Because if you look at the 2 numbers here that we're multiplying, you can see that one has 3 significant figures and the second one has 2 significant figures. Therefore, the result of this mathematical operation in this case should have only 2 significant figures. For addition and subtraction, the number of significant figures in the result depends on the number of decimal places in the least accurate measurement. So if we look at this example here, we can see the first number, or the first term, has 1 decimal, while the second term has 3 decimals. So if we use a calculator to add these 2 numbers together, what we get is a number that has 3 decimals. This is because the calculator assumes that the missing decimals in the first term are all zeros. And mathematically that's quite correct. But in terms of significant figures, it isn't. We see that the result, in this case a sum, should have only one decimal place, because one of these 2 terms has 1 decimal place, the other one has 3. Therefore, the first one is the least accurate measurement, and our result cannot be more accurate than the least accurate measurement. In other words, our result should have 1 decimal place, and we have to round off the result from the calculator to the first decimal place. So we obtain 18.7, which incidentally contains 3 significant figures, but we don't look at the significant figures while we're adding or subtracting. And so this sort of summarizes things: 1 decimal place, 3 decimal places, and 1 decimal place. Okay, in this exercise, we're combining both addition, subtraction, and multiplication, division. And if you look at it carefully, of course you start with the difference or subtraction. You just follow the rules known as BEDMAS, if you remember. And so this is actually, the way it's written here means there is a parenthesis around here, and we could write it in if you want to put it in, but you don't really need it. You know that when you write something like this, there is an implied parenthesis here. And so this is the first operation that you carry out. In other words, you first subtract 0.567 from 1.23 grams. And when you do that, what do you obtain? You obtain 0.663, which should have, according to our rules, only 2 decimal places. And this is why I put here a little underscore, just to show that this number is only good to 2 decimal places. I'm keeping the third one because when you do a series of operations, you shouldn't round off at every step, because your result becomes more and more inaccurate. And now we take this value, the difference between the 2 numbers, and divide it by the bottom number, by the denominator 0.34442, which now contains, we see it contains 5 significant figures. Of course, in this case now we're dividing 2 numbers and we just look at significant figures. And when you do that, you see that the number, the numerator, has actually only 2 significant figures. Remember that it is good only to the second decimal, and the denominator has 5. Therefore, the quotient or result should have only 2 significant figures. And so when we actually perform the division, we get a number such as 1.924, which we then round off to the second significant figure, and so we have 1.9. And if we pay attention to units, it's going to be 1.9 grams per meter. What is the reliability of a measurement? There are 2 ways to assess the reliability of a measurement. One is the precision of the measurement, which is a measure of the reproducibility of a measurement and describes the agreement of the results within a set of measurements. What do we mean by that? Well, let's say that you weigh an object 10 times in a row. You'll find that if you have a fairly sensitive balance, the result that you'll get after every measurement will not be exactly the same. There'll be a certain variability. And the greater the variability, the less the precision. The closer the measurements are to each other, the more they agree with each other, the greater the precision. Another experiment you could do is you take 20 people in a classroom and give them a stick and a ruler and ask each one of them to measure as best they can the stick and write down the result. When you collect the results and compare them, you'll find that the results do not agree completely with each other. They're not all the same. There's some variability again. And once again, the closer the results are to each other, the greater the precision of the measurement. Another measure of reliability is the accuracy of a measurement. And the accuracy is a measure of the agreement of an experimentally obtained value with the true or accepted value. So, if we go back to the balance example, let's say you weigh an object 10 times. You have a certain variability, and in order to account for the variability, you actually take an arithmetic average of the 10 measurements. So this average is intrinsically a better value than the individual measurements. And now you compare this average to some accepted value, that is, a value that is known from some other experiment for that weight or mass that you measured on the balance. And if your experimental value agrees with the accepted value closely, then you say that it's an accurate measurement. And if it doesn't agree closely, it's not an accurate measurement. Accuracy is not always available because in science very often what we're trying to measure or find out is not really known, and therefore there can be no accepted value. The precision can always be measured simply by seeing how reproducible a measurement is. Here is an analogy in which we look at a dartboard with some darts on it. And let's say that the accepted value is the value of the bullseye, and all the other parts of the dartboard have their own values depending how far away they are from the bullseye and in what direction they might be. So if you look at the first instance here, denoted by A, what would you say the result of the experiment is? Each dart is an outcome of the experiment. So we have we actually do the experiment 3 times and we look at the outcome. Well, you'd say that for this first experiment, you'd say that the measurement was fairly precise because the darts are pretty close to each other, and definitely 2 of them are in the bullseye and 1 is very close. So the experiment is also accurate. It's accurate and precise. For B, the situation is quite different in one aspect, and that is all the darts are very close to each other. They're very far from the bullseye. And so you see right away this experiment is, or the result of the experiment is very precise but far from accurate. So you obtained, if you will, a set of measurements that agree fairly well with each other but give you the wrong answer because they're very far from the accepted value. And finally, if you look at the third experiment here, the darts are far apart from each other and none of them is on the bullseye. They're all quite far from the bullseye as well. So this experiment is truly a poor experiment. It's neither precise nor accurate. The one in B appears to be a good experiment, but it's also poor because the results do not agree with the accepted value. The only good one really here is the first one. Dimensional analysis is at its simplest a method of unit conversion. And this method is often referred to as the unit factor method. In the unit factor method, one first establishes an equivalence statement, and this equivalence statement usually gives rise to 2 unit factors. Let's look at a concrete example. 1 inch is equal to 2.54 centimeters exactly. This is an equivalence statement. It says that 1 inch is equal to, or even better, equivalent to 2.54 centimeters. They represent the same length. And if we divide now the left-hand side by the right-hand side, we obtain 1 unit factor. And when we divide the right-hand side by the left-hand side, we obtain the second unit factor. And that's all there is in this case. They're called unit factors because, as you see, although 1 over 2.54 is not equal to 1 mathematically, but if conceptually 1 inch is a length that is exactly equal then the length of 2.54 centimeters. And therefore, the denominator and the numerator are equal to each other conceptually. And this is why this sort of quotient is called a unit factor. In this exercise, we'll use the unit factor method to convert 8 meters to inches. We're given one equivalence statement. We're told that 1 inch is equal to 2.54 centimeters exactly. This, however, does not allow us to convert it in meters to inches because we don't have an equivalent statement here relating meters to centimeters, so we can't go directly from meters to inches. So we need some equivalent statement that will relate meters to centimeters. And it's not given because we expect to know it. We know that 1 meter is 100 centimeters. So this is our second equivalent statement. Now, for the unit factor method to work properly, we must have a continuous pathway between what we start with and what we're trying to get. In other words, we must have at least one unit that is the same for each equivalent statement. And so here we see that as we go from meters to inches, how do we do it? Well, we can go from meters to centimeters, and then from centimeters to inches. So that is a continuous path, as you can see. Now, let's do it. Here, we start with what is given to us, 8 meters, and then we apply 2 successive unit factors such that we obtain inches at the end. So let's see how this works. This is what we do. We start with 8 meters, then we multiply by the first unit factor, which is 100 centimeters divided by 1 meter. This allows us to cancel out the meters, and then the product of these two numbers is actually the length of 8 meters expressed in centimeters. And then we divide by centimeters, by 2.54 centimeters, and multiply by 1 inch. This unit factor we obtain from this equivalent statement. So in this case we had to divide the right hand side by the left hand side, and in this case the left hand side by the right hand side. Again, we choose our unit factors as we need them so that we obtain the cancellations that we need. Meters here cancel out, leaving centimeters, and in fact 8 meters are equal to 800 centimeters. Then we cancel out the centimeters to produce inches. And in the end we obtain our final value, which is 314.9 inches, or again, if we do that to if we actually round off to 3 significant figures, because our given experimental value has 3 significant figures, we obtain a final result of 315 inches. Remember, this is a metric conversion. It is exact, and each number here has conceptually or in theory an infinite number of significant figures, and therefore the 1 here and the 1 here do not in any way limit the number of significant figures in the result. We just look at our given measurement. Let's do one more exercise. This is sort of the problem you find in high school books, but we're going to try to solve it using the unit factor method, which is the ideal one to convert from one unit to another. So what we have here is, it says what would be the cost in dollars of nails for a fence 88 feet long if one needs 9 nails per foot of fence. There are 36 nails in a pound and they sell for 69 cents per pound. So we're trying to find the cost in dollars of the nails for an 88 foot long fence. And so we have to find a continuous path that goes from feet to dollars. And this entails setting up a series of equivalent statements. So let's see what we can do. For instance, we can equate 1 foot of fence to 9 nails. So we can say that 1 foot is equivalent to 9 nails. This is from the first statement here. The second statement, there are 36 nails in a pound, allows us to relate nails to pounds or pounds to nails, and so this would be our second equivalent statement. 1 pound is equivalent to 36 nails. And finally, we have this statement here that every pound sells for 69 cents. And therefore, we can now set up the equivalent statement that 1 pound is equivalent to 69 cents. Now, so far we do seem to have a continuous path going from feet to nails, from nails to pounds, from pounds to cents. And we need now one more equivalent statement relating cents to dollars. Again, it's not given because it is fairly widely known that $1 is equal to 100 cents, and therefore we put that in as our last equivalent statement. Now, if you remember, in the previous exercise, I mentioned that to have a continuous pathway, one needs to have two identical units in equivalent statements. So, for instance, in these first two equivalent statements, the nails are the common unit. In these two equivalent statements, the pounds are the common units. And finally, if you take this one here and the last one here, the cents are the common unit. This allows for a continuous path. And as we said, now we can go clearly from feet to nails, from nails to pounds, from pounds to cents, and from cents to dollars. And this presupposes right away we're going to use 4 unit factors, one each for every equivalent statement. And so we start with what we're given, 88 feet, and then use conversion factors or unit factors to go from feet to nails, nails to pounds, pounds to cents, and cents to dollars. So let's do it here. This is the series of operations, and as you can see, in the first one, we convert feet to nails, we cancel out the feet, and we obtain nails. Now, this product here has a meaning, of course. It simply is the number of nails required to build this 88-foot fence. Then, as we now go from nails to pounds, we cancel now the nails. And again, the product of these 3 factors also has a meaning. It is simply the weight of the nails in pounds that are required to make the 88-foot fence. Now we go to one more conversion. We convert pounds to cents. So here we divide the pounds by pounds and we obtain cents. Again, the product here of these 4 factors has a meaning. It is simply the cost in cents of the nails required to make the 88-foot fence. And finally, we make one last conversion in which you go from cents to dollars, and we obtain in the end the cost in dollars of the nails required to make the 88-foot fence. And you see, I've written my result or product to 2 significant figures simply because my initial value is given to 2 significant figures. There are 9 nails per foot. That's obviously an exact conversion. We counted the nails, and you can see that in the majority of cases here, we could actually say that they're all exact conversions. Certainly, if a pound costs 69 cents, it doesn't cost 67, 68, or 70, so it costs 69. So it's an exact number, and of course, the conversion from $1 to 100 cents or 100 cents to $1 is also an exact conversion. The unit factor method is a method of guided proportions. But it has an advantage over proportions in the sense that the units guide us. So we can see clearly how we go from a given unit to a desired unit by unit cancellation. In other words, we multiply the given unit by some unit factor, which is derived from an equivalence statement between the given unit and the desired unit. And we can see how the given unit cancels out and we obtain the desired unit. All right, let's briefly look at density, which is a physical property of a substance. And density is defined as mass per unit volume. So essentially, it is the quotient of mass and volume. And the way to determine a density is to take a fixed volume of a substance and then weigh it, and then we divide the mass by the volume. In this exercise, we're given that a mass of 182 grams of benzene fills a measuring cylinder to the 2007 milliliter mark. In other words, we're told that 207 milliliters of benzene weigh 182 grams. And we're asked to calculate the density of benzene and express it in grams per cubic centimeter and in kilograms per cubic meter. And the first one is very straightforward. It's very easy to get grams per cubic centimeter. The kilogram per cubic meter may require a little thought. But anyhow, I'll leave this exercise to you, and so please attempt it. The answers are given here. So you'll see when you complete your calculations whether you got the right result or not. Well, I think this completes part 1 of Unit 1. So thank you, and I'll see you for the next lecture.